This tiny chip is an inertial measurement unit. It's only 3 by 2.5 mm, but it contains an accelerometer, a gyroscope, and a temperature sensor. I actually have two different ones, one from TDK InvenSense and another from STMicroelectronics. In this video I'm going to solder both of them onto a custom PCB and try to read data from them at the same time using Raspberry Zero. And I'm going to use codecs to generate Python scripts to process the data. To design the PCB, we first need to understand how these inertial units work. The easiest way to find the datasheet is to go to DigiKey and open the components page. From there you can usually jump directly to the manufacturer's datasheet. Here is the datasheet for the ICM unit. One of the first things we need to check is the operating voltage. This sensor supports up to 3.6 volts, which means we can power it directly from the 3.3 volt pins on the Raspberry Pi Zero without any level shifting. The application section is where the datasheet becomes really useful for PCB design. It shows the recommended circuit, including the decoupling capacitors required for stable operation. I usually write these components values down so I can order them later when assembling the board. The pin-out diagram tells us how to configure the chip for different communication modes. For example, this pin needs to be pulled high if you want to use I2C instead of SPI. Another pin allows us to configure I2C address, which is useful if you want to connect multiple sensors to the same bus. The same process applies to a STMicroelectronics sensor. We go through the datasheet, check the voltage requirements and extract the recommended schematic for the PCB. After extracting the required components from the datasheet, I recreated the recommended circuit in the EasyEDA. Each inertial unit needs a few basic things to operate: power, decoupling capacitors, and the communication interface. First is the power supply. The sensor runs from 3.3 volts, and the datasheet recommends adding small decoupling capacitors close to the chip to stabilize the power. Communication happens over I2C, so both sensors share the same SDA and SCL lines. Because both devices sit on the same bus, we configure the I2C addresses using this pin, so the Raspberry Zero can talk to them individually. I also added a zero-ohm resistors between each sensor and the I2C bus. A zero-ohm resistor is basically a tiny jumper that lets me decide whether a component is connected or disconnected. This allows me to connect either sensor or both of them together on the same bus. It's a small design trick that makes debugging much easier if something doesn't work. After finishing the schematic, I moved on to the PCB layout. Since this was my first attempt at building custom PCB, I kept the design fairly simple and used a 2-layer board. The ground plane is shared across the board, which keeps the electrical noise down. And this is what the board looks like in 3D view. A few days later, the PCB arrived. This is the small PCB that hosts both IMU sensors and their supporting components. The solder paste I had was quite old, so before using it I mixed it with a bit of flux to bring it back to usable consistency. For these tiny chips I start by adding a very small amount of solder paste to the pad. It should almost feel like it's not enough. Then I place the IMU chip and the surrounding capacitors on the board. After everything is positioned, I add a little more flux on top and use hot air to reflow the solder paste. Once the chip is soldered, I checked for bridges between the pins using my multimeter in continuity mode. I probe across pins to make sure nothing is accidentally shorted together. I repeated the same process for the second IMU sensor on the other side of the board. After After soldering, I connected the board to Raspberry Pi Zero using the I2C pins. Running I2C detect confirms that both sensors appear on the bus with different addresses. To read the sensors, I asked Codex to generate a simple Python script. The script pulls both IMU over I2C and prints their readings to the console. Once the script was running, I could see the values change as I moved the board around. Both sensors are now working simultaneously on the same I2C bus. With both IMUs running, this board will become the orientation sensor for the RC car Autopilot. The goal is to tell the car which direction it should go and let the control system keep the vehicle on that heading automatically.